Hello, everyone, and welcome to our first webinar. I am Zali, engineering student at University of Oklahoma, and I will be your moderator for this amazing webinar. Our webinar today is about Introduction to Quantitative Research Design and Process, which will be presented by Dr. Hasan Almekdash. Dr. Hasan is a Director of Statistical Services Senior Biostatistician at Texas Tech University. Dr. Almekdash's current research interests include the application of data science in healthcare, advanced biostatistical modeling, the application of quasi-experimental design and GIS, spatial analysis and epidemiological research, and institutional evaluation and assessment. He was recognized on the state and national levels as quantitative methodologist and statistician. Dr. Almekdash is an educator with more than 15 years of teaching experience in higher education context in the United States and internationally. It is our pleasure to have you, Dr. Hasan, today, and the mic is definitely yours.
Thank you all so much. I hope you can hear me well. Let me know if you can't hear me well. So is it clear? You can all hear me?
Yes, we can.
Okay.
Yes.
First, let me thank Arab Oil and Gas Academy for hosting me. I really like this initiative. It's a great platform to exchange great ideas internationally. So I know that we have audience from all over the world, and that's really interesting. I'm happy to be with you today. So this lecture is going to be about quantitative research methods. It's an intro. I assume that the level of the audience is introductory, so we are not really gonna talk about advanced things today. We are gonna talk about the basics that will help you become a researcher in the future. Of course, this is an ocean of knowledge. You know, when you say quantitative research methods, you're talking about thousands of statistical techniques. You're talking about mathematical models. You're talking about different styles in research and all of that. So we need a way to break it down into like simple things that will help us start. So many people think research or doing research is, you know, genius. You need to be some sort of genius, or you need to be like highly talented to do research. Well, that's true in some instances, but actually it's a simple process. You need to learn this process and understand its components, and then you can do research. So let's start. Today, my agenda for the lecture, I'm going to talk about research paradigms, types of research, think variables, frequently used quantitative designs, causal comparative designs, correlational designs, and then I will talk about the research process in a simplified way. I will talk about topic selection, reviewing the literature, developing research questions, and designing the study. So let's start with our presentation. So we need to understand the basics. So doing research has to do with how you view the world, philosophies. So we have something called research paradigms, which is like philosophies of viewing the world. So how you view the world, like as a statistician, I view the world as like numbers, mathematics. I think that math and numbers can model everything, can help me answer research questions. But my qualitative researchers, colleagues will tell me, no, numbers are not enough to understand the world. The world is more complex and chaotic that can't be modeled by numbers. So you see, these are philosophies about viewing the world. So a research paradigm is belief about the nature of knowledge, how you think knowledge can be generated, how you think knowledge can be presented to the world. It has to do with your assumptions. So as I told you, you assume I can model everything. You know, I know mathematics, I know calculus, I know probability theory, so I can predict everything going on. Maybe that's what you think about the world. So it helps you guide thinking and the research process. So that's very critical when you think in a specific way, when you think that, okay, math and numbers can explain the world, okay, that will guide everything in your research. The methods you will use, how you will design the research, what type of literature will you look at, and how you will synthesize it and review it. So it's a framework of methodology, and it's a criterion of validity, how you consider things valid and they work and worthy to share with the world. So what are the common research paradigms? When we talk about research paradigms, we have, a few common ones. These are philosophies, and I highly recommend you understand them in depth. So today we are touching on them. We are not going to explain them in depth, but really I will tell you why you need to understand them and why they are critical. So you have positivism, postpositivism, constructivism or interpretivism. You have transformative paradigms and pragmatism. So positivism, it's the scientific method. You make observation, use deduction, and you make notes. You try to model phenomena. You try to describe it in numbers. You are not biased. You are very objective about what you observe and what you do, what you report. Math can explain the world. It's quantitative. So most quantitative folks, such as engineers, people like you, are positivist. Measurement and observation. So this is critical thing in positive paradigm. It tests theories. So you test things. You look at something, you observe, you look, you notice something, you take notes, you write research questions, you start testing things to confirm what you observed or not. Now, post-positivism is like positivism, but it depends on theories constructed before you. So well-developed theories in your field, in your area, affect research and examined problem. So you do not look at things aside. You do not observe things just naturally. You have a theory that that guides your research. So research design, data collection and analysis, interpretation are influenced by theory because the world is multiple and ambiguous. So what that means, people who are post-positivist will feel lost just looking at data and numbers and running the algorithms and analyzing data and reporting findings. They will feel, it's like chaotic. Something is missing. I need a well-developed theory to guide me in all these processes of data collection, analysis, and interpretation. So this paradigm can be quantitative or qualitative. Qualitative, design has, let me simplify it. It's not our topic today. It's analyzing non-numerical data. Let's agree on that. Qualitative. Constructivism or interpretivism, its reality is socially constructed. So reality is not one, there is no one reality. Reality varies in the world based on who is defining reality, who is looking at reality. So there is no one real thing. Understanding the human experience, so human is central, our experiences as people is central to this paradigm, does not start with a theory, and theory is constructed by research. So you develop the theory while you're doing your research, and it's mostly qualitative. Transformative paradigms, it's about policy and political agendas. They are important in this paradigm. Contains an agenda of reform. You will use these paradigms if you worked in institutional, for example, assessment, you want to evaluate your company or university. Previously developed theories and paradigms can be biased due to political and cultural reasons. So here, this paradigm does not isolate research from bias or political agendas necessarily. Can be qualitative or quantitative. Mixed methods are the methods that put together qualitative and quantitative research. So why use quantitative and qualitative in this paradigm? Because you can use different lenses at looking at reality. Pragmatism, no commitment to philosophy paradigm. Just do whatever needed to answer RQs, research questions. The research problem is central and it applies to all aspects of understanding the problem. So the most important thing is the problem you are investigating. You are not looking at philosophies, at what research theories are there, what theories, content field or area theories are there. You're trying to solve a problem. That sounds like most engineers, correct? Some researchers view it as the underlying paradigm of mixed methods. So why I touch on paradigms? Because of real life scenarios. So educational contexts are ideal. So as an engineer, you use maybe quantitative modeling most of the time. You use mathematical modeling most of the time. But when you are in real life, you are in a company or institution, you don't know what comes to you. So that happened to me in real life many times. So you are analyzing, let's say, scientific data, but then your boss or your supervisor asks you, I need to evaluate our production. I need to evaluate our employees. I need to evaluate the processes, the policies we put. So you really need to know something about everything and then master one thing. Engineers, statisticians, and data scientists are positivist and pragmatic folks. Mostly we are about numbers, scientific method. We are pragmatic, we try to solve problem, but you don't really know if you are going to need other paradigms in your research and professional career. So basically you need to have some ideas about them. And when you do research, let me tell you, I have a friend who is a faculty in engineering. So he got his PhD from the United States, and he is a very good engineer and scientist. Now, the first assignment he got as a professor in his university is to evaluate the pre-engineering curriculum. So he needed to do, this is new to him, it was about survey research, it was about surveying the students in a big university, and he needed to move within paradigms and research methods to achieve this task. So I'm just telling you. So now let's touch on types of research. So when we say research, what do we mean by research? We have these major types. We have basic or fundamental research. Well, this is the new knowledge generating research. The big theories, the ideas, the discoveries. It's experimental. It's run under very tight, controlled conditions. And it's the most rigorous. Rigorous means difficult. It needs time, and efforts, resources. So big ideas, when you hear like something about the black holes in the space, and they discovered like something about the gravity of black hole or the matter composing some stars, like this doesn't have now like maybe relevant real application, but this is basic research. We can use it to develop many things in the future. Applied research, it's practical, tackles real life problems and solutions. It takes more natural settings than the lab controlled settings or the experimental settings sometimes. It uses ideas from basic research. Action research, related to practice. Answer question in their local settings. Great to solve your company's problem. So sometimes we need to do research, like my friend who is a faculty in petroleum engineering. I told you about him. So he did action research and evaluation research somehow to solve problem and evaluate the curriculum in his institution. When you look at problems in your company, like you see a problem or your institution, and then you do research to solve this problem. This is action research. It has to do with the local setting, I mean the institution you're in, the company you're in, etc. Evaluation research, the name tells about it, evaluates a process, worth, new product, your institution or company policies, etc. So that's good to evaluate things. Summative evaluation and formative evaluation. So to say something is working or not, or to give feedback how something can be working better or more functional, etc. Now, orientational research, research conducted to advance a previously held ideology. Now, whenever I introduce orientational research to students, oh, they feel it's, oh, weird. You have an ideology that you need to advance a cause or political agenda or to defend an orientation. Now, many research in the social sciences, environmental research, like they sometimes are orientational research. Now, why you need to understand these paradigms or these types of research, so you really know what you're doing. So are you orientational? Are you defending something? Okay. Some people might say, oh, that's biased in the basic sciences. Okay. Like, but in the, let's say, social sciences and business and administration, sometimes you need to show a viewpoint. You know, this is a previously held ideology and let's say scientifically defended or empirically defended. Now we get closer to quantitative designs. So how to become a statistician or a quantitative methodologist? That means a statistician that works in research, puts methodology for research, the easy way. So these are two great statisticians, famous. This is Sir Ronald Fisher, and this is Gertrude Cox. And I think if you worked in statistics enough, you will know Fisher and Cox. These names are very, very well known. So how to become like them? So one way is to dig deep into the math of statistics and to understand all the functions, like this function you see here, and then understand some probability theory, understand some, you know, calculus maybe. So this is how traditionally statistics is taught, okay? I have this way is to think variables. So what I mean of thinking variables? Well, there is a famous statistician, very famous, you know. His name is John Tukey. He is a well-known American mathematician and statistician. He said, if you are a statistician, you can play in everybody's backyard. So what he means by that, if you're a statistician, you can play in everybody's backyard. That means statistics is a transferable skill that you can transfer to any field or to any area of science, or whether it's hard science, social science, business, administration, whatever. And why statistician can work in any field? Because we think variables. We view any, like if you tell me now about your interest in research, I will start to think about variables and how they work together, how they interact, okay, what you are trying to predict, what you are trying to compare, etc. So what you really need to know, this is a piece of advice to you all guys when you start research and you start learning statistics and you start to see thousands or hundreds or thousands, you know, actually, of different statistical models and complicated terms. You need to know what test model is suitable for the variables you are collecting or you are looking at and their characteristics. What the test model does in relation to the variables. So this model, okay, what it does, how it works, what it tells. Does it help me see a relationship? Does it help me compare groups? Does it help me classify, like do classification? Does it help me like tell you an increase in X leads to this increase in Y, etc.? how the variables are defined in the test model and in what structure. So how to build the model in software. So basically, yeah, now I know generalized estimating equations model. Oh, I'm happy. Okay. So how to build it in software? If you, whatever software you're using R, Python, MATLAB, SPSS, how I can build this model with these variables I have now. Finally, how to interpret the test statistics and model parameters and what you exactly need to report in a scientific paper. So why I am giving you these 4 points? Because whenever, like in the future, when you start learning about models, like advanced models, say you're going to study hierarchical linear models, okay? Hierarchical linear models. Okay, what is that? So before you do anything, remember these 4 points. What is suitable for, what variables I can use, what the characteristics of the variables, how they should be like organized, what level of measurement, what the test of model or what the test or model does in relation to variables. So what it does, predict, compare, etc. How the variable are defined in the test model. Now I need to build it. So to use it, okay, and I need to know how to build it in a software, right? And how to interpret the test and what to report. Now, why what to report is important. Sometimes you run a test and you get like many model parameters and many statistical tables, and you get test statistics, etc. So basically, you should know in your field what you need to report from all that huge output. Now, what I mean by think variables, of course, I simplified the same thing. It's very simple and easy here. There is a lot to that when we talk about variables and type of like level of measurement, etc. But what we need to know, variable is a condition or characteristic that can take different values or categories. So different values like temperature, like your college GPA out of 100, like blood pressure, like reservoir pressure, production. These are like variables, right? Or categories. Now, categorical variable is classes, categories such as gender, male, female, ethnicity, maybe oil, well, location, country, you know, country 1, country 2, country 3. These are categories, right? Like gender, male, female, this is category. So variables in general can be categorical or quantitative. But before I talk about quantitative and categorical, a constant is single value or category, as you know, of a variable. Example, the category male and the variable gender, the constant does not vary. Okay, what we mean by a quantitative variable, also known as continuous. So you need to know these terminology when people say quantitative variable, continuous variable, scale variable, values that can vary on a scale, temperature. Categorical variable, different types or categories of a phenomenon. Example, ethnicity, gender, country of origin, oil well location, methods of production. So if you have method 1, method 2, method 3, these are like categories, right? Now, 2 important things to know also when we talk about statistics and modeling, independent variable and dependent variable. So an independent variable, it's variable X. It's the predictor or the exposure or factor or cause, the cause, you know, the cause of something. What causes the change in the outcome. So this X variable can be called, in some papers you'll see, they call it independent variable, then exposure, factor, the cause, what causes the change. It's the same thing, independent variable, X. Dependent variable is the Y variable, the affected by X, it's the outcome or the response variable. Okay? Now, the two most frequently used types of statistical designs can be easily understood if we think variables. Okay. So we have the causal comparative designs. What do we mean by causal comparative designs? The primary independent variable of interest is a categorical variable. So it has classes or categories such as gender, country of origin, location. The dependent variable is usually a quantitative continuous variable. Okay, so here now, let me tell you, if I want to compare between two countries on income, so do people in country A make more money than people in country B? So here the independent variable is country. I have two countries, right? A and B. And the dependent continuous variable is income. So what we are doing in these models in general, the averages of the dependent variables are compared among the categories of the independent variable to conclude if there are any statistically significant differences among the examined categories. So now my question is about countries and income. I want to see if people in a specific country, between two countries, are making more money. So I'm comparing the average in country A and the average in country B, and I'm trying to see if this difference, if any, of course, is statistically significant or not. So maybe if I got like average income in country A, $50,000 a year, and then in country B, $51,000. So this difference, is it statistically significant or not? Well, most likely not, right? So example, IV, independent variable 1, we have oil well locations. IV variable 2, production method, and then production rate. So I have two oil production methods. I'm not an oil engineer like petroleum engineer. So basically I'm trying to bring an idea, but you are the guys who can find ideas now about these research designs. So I'm trying to see if one production method is more effective, okay, among 3 oil well locations. And what I'm comparing, okay, production rate. Now, this is the idea, the general idea of these models, okay? It's you are comparing groups on a continuous or scale variables, okay? Example tests and models, I'm sure you've heard of these or at least some of these, t-tests. And I say tests because there are 3 types of t-tests, like 3 use types, ANOVAs, okay? ANOVAs, we have one-way ANOVA, two-way ANOVA, repeated measures ANOVA, factorial ANOVA, ANCOVAs, MANOVAs, MANCOVAs, factorial designs, and mixed factorial designs. So in your PhD or master's, research design class, when you see one of these, know that the main thing is you are comparing groups on continuous variables. That's the basic and simple idea. So in t-tests, you are comparing 2 groups on a continuous variable. In ANOVA, you are comparing more than 2 groups on continuous variable. In ANCOVA, you are comparing more than 2 groups on a continuous variable, but there is another variable that is a covariate. It intervenes in the relationship. Of course, we will discuss these in the future in depth if we have, an occasion to talk about these and explain how they work, as I told you in the 4 pieces of advice. But whenever you see these, so not to get lost, especially when you start to talk about multivariate analysis of variance or multivariate analysis of covariance, the MANCOVA, basically I'm doing one thing. I'm comparing groups, a categorical variable, or categorical variables on continuous variable, averages of continuous variables. Correlational designs. The primary variables of interest are continuous variables. So the primary variables of interest are continuous variables. X and Y, two scale or continuous variables. Example, initial reservoir fluid pressure and production rate, right? I know that, like, and correct me if I'm wrong, that more production, like the less initial reservoir fluid pressure. So there is negative correlation relationship between them, maybe. So when you look at variables that are continuous, or like most of your designs are correlational, you need to see if increase in X leads to increase in Y, or if there is an opposite relationship, or if X can really predict Y after controlling for some other variable. So what I want you to know, and that's important, when you hear these tests, most of these tests deal with this principle, like correlational design. Correlations like Pearson R, you know, correlation, Kendall-Stowe, Spearman-Rowe, linear regression models, and I say models because, you know, regression can take different forms in different models. Some mixed models, okay? These are advanced and complicated general linear models, hierarchical linear models, generalized estimating equations, structural equation models, path analysis, process analysis, principal component analysis, factor analysis. By the way, principal component analysis is like family member of factor analysis, ISTRA. So now maybe you don't know these models and how they work, or at least not all of them. But now you understand the main thing is you are looking at, you know, XY relationship that are continuous mainly, and linear equations, mostly linear equations. Of course, we have nonlinear equations, but mostly linear equations. Now, the research process simplified. So we talked a little bit about the quantitative designs. Now I will talk about the research process. So how we do research. Like, this process simplifies the whole thing to you. First, you need to select a topic, review the literature, develop questions, design study, collect data, analyze and interpret data, report findings. So I will only highlight the four first ones here. So select topic. So what I'm going to research, what I'm going to do, or what topic I'm conducting research on. So is the initial questions, or the question you're initially asking, you know, you start with some question about the world, too broad? Is it like general? So sometimes people may ask, like, especially like people in their beginning in the career of research, ask, okay, I think production method A, okay, is the best. Now that's a bad research question. Why? Because, you know, this is very general first. Like, what do you mean exactly by the best? The best in what? And the best, how you measure the best. Always as a researcher or as a methodologist or statistician, I ask how we can measure things. So how you can measure the word good? Like, okay, what is good to me might not be good to you, good perceived differently among scientists and people. So this research question is bad, okay? So a better research question would be, extraction method A will increase production rate by, and you state the amount, okay? So here, oh, we can measure it. It will increase production rate, which means it's better than conventional methods, for example, but do not use words that are general and that can't be measured objectively by scientists. So this is number one. Can the problem be investigated? So is it feasible? Can you really investigate what you are asking? Because sometimes we can ask great questions, you know, but you can't investigate them because they need a lot of resources, time, or it's not possible to measure, okay? Like, I want to investigate if there is oil in the furthest star in the solar system, okay? Oh, okay. That's good, but not feasible for me at this level. Or maybe in another galaxy. So what I want to tell you, make sure that your problem can be investigated. Can the data be analyzed? Okay, if you collect data, can you analyze the data? And is the problem significant? Is the problem gonna add to what we know? Your answers to research question will significantly benefit humanity, the industry, education, whatever you're working on. Can the results be generalized? You know, so as quantitative scientists, we are interested in generalizing our statistical findings on the sample, on the entire population, right? So can you do this when you are conducting research? What costs and time are involved? You need to think about these significantly. Do you need funding? Do you need to apply to grant to do your research? Are you going to give results in reasonable time, timely manner? Is the approach appropriate? So say you are doing experiment, is it appropriate to answering your research question? Is there potential harm to subjects? Of course, this is when you have people in your experiment, or you have human beings in your experiment, or even animals. Sometimes, like, you need to think about ethical consideration when you are doing research. So basically, if you don't have people in your research, you don't need to think about that. If you have people, you need to think about harm. And harm is not only physical, because you are doing some, let's say, biological or biomedical experiment. Harm can be psychological or emotional. It can take many forms. So you usually consult with the IRB in our universities, right? The Internal Review Board. These people are the best to ask them about potential harm to subjects if you have human subjects in your research. Now we move on to reviewing the literature. So start your search based on the identified topic. You identified your topic now, you start your search, familiarize yourself with the search databases. So basically, like, go to your librarian. Really, there is a resource in libraries here in the United States, at least I know about that. Like, the librarians can really help you and give you some training on how to use different databases for search. Skim articles to identify relevant ones. So of course you identified, say, 25 articles. You're not gonna read them, like, you know, sometimes articles can be really thick and time consuming. First, you read the introduction, you read the abstract, you read the conclusion. You need to decide, is this article important to be read, or I need to dismiss it? I don't need to read it. Categorize the articles based on area and relevance to your project. So in the literature, you need articles about the topic, right? You're doing like fluid pressure and reservoirs. Then you need articles to support your methodology, your research design. Whatever articles you need, categorize them. These articles to talk about fluids. These articles to talk about production. These articles to talk about methodology. Read the articles critically with your analytical lenses and take notes. So basically, do not trust that everybody written before me is great and I need, no. Read it critically. You are a scientist. You're a researcher. So what you are doing is you're evaluating what's written before you, not only summarizing it. Yeah, because I see some published paper, I need to be like summarizing it and not thinking about what's in it. No, read it critically with a critical lens. Write an annotated bibliography. This is optional. So what is an annotated bibliography? It's you cite the paper you're working with, and then you write a paragraph about it. In this paper, researchers collected data about A, B, C, D, etc. They did this to the data collection, cleaning. They used these methods to analyze data, and they found the following. So it's a summary. It helps you synthesize the literature. It helps you like see the literature when you do it, when you write a paragraph summary about each article, to see the literature more clearly. Oh, I think after writing this paragraph about this article, it's not very relevant to my research. Write a coherent critical review. So what is the literature review? It's not just a summary, it's critical. You are criticizing what's been done, you are showing what's been done before you, you are putting it all together, you are criticizing it, you know, in a constructive manner, and you are identifying the gaps. So why you are reviewing this literature? You want to show the gap that you are working on now and you are asking research questions about, and the problems you are trying to find solution. So always summarize your literature. It starts like this, narrow it down until you reach the gap. That's why you need my research. That's why you need these research questions answered. Make sure to be familiar with the style guidelines. Of course, that varies by field. So when you write, always learn the style people use. So for example, this is Dr. For example, Al-Garihi can help you with what style used in engineering. So I know what style is used in medicine, in biomedical sciences. I know what style used in, for example, psychology. So these styles in the social sciences are different. So make sure you know the style guidelines when you write your lit review or your research paper. Write your RQs. That's very important. Like RQs, research questions are highly important. So hypotheses or hypotheses versus research questions. So, you know, when we do research, quantitative research, usually like if you are testing hypotheses, you start by writing a testable hypothesis about phenomenon. It's a formal statement. So it's not a question, it's a statement of the researcher's prediction of the specific relation that exists among the examined variables, okay? So you expect a relation, and then you write what you predict, okay? Method A in extraction will improve production rate. Now, all your research is either to prove this or disprove it. So how we write the script, possible script, maybe this is possible script. Group A participants will differ in some way, increase, decrease, or improve on dependent variable, okay? On a variable that you are measuring from group B participants. So let's use participants. Students who watched Dr. Almekdash Hasan lecture will improve on research methods and design from people who didn't watch the video. So that's funny, right? But this is a hypothesis. Group A and B, remember, are levels of the independent variable. It's a categorical variable, and these are the levels. A hypothesis must be capable of being confirmed or not. So when you write your hypothesis, look, can I prove it or disprove it? Can I confirm it or not? If you can, that means, okay, you possibly have a very nice, well-written hypothesis. Research questions can be descriptive, predictive, or causal research questions. So let's touch on that. So descriptive research questions have to do with descriptive statistics. When you start looking at how the world is described in number, you summarize data and means, standard deviations, medians, interquartile ranges, the percentiles, etc. So it answers questions such as how much, how frequently, how often, what change over time or over different situations is happening, okay? So these are called how much, how frequently, how often, etc. The descriptive dimension. So you start, usually, you start with the descriptive dimension. Does participants, variable states in verb form at research site? So what is that exactly? So how much is a descriptive dimension? Do engineers, okay, earn, okay, in country X, okay? How much do engineers, of course, on average, earn in country X? This is like a possible descriptive question. And you usually, like the first question or couple of questions in your paper is usually descriptive. It identifies the degree of relationship between two variables. So correlation, when you do correlation, like the Pearson R, right? Correlation, and you report it to the world, like you are looking at, this is descriptive. This is not a hypothesis test yet, or even parameter estimate. You are just looking at relationships. So questions should be clear. Like if someone reads the question, or if you tell someone your question, he, she should know that you are doing correlation. Is there a relationship, association, shared patterns or behaviors between variables X and Y? Okay, that's the descriptive research question. Predictive research questions ask if one or more variables can predict some future outcome. Okay, so can the number of hours you watch a webinar, you know, the lectures we are giving, predict your quiz scores? You know, you have quizzes, like something like that, okay? As I told you, pressure, can pressure predict production rate? I don't know, Dr. Garihi can tell you. But this is what I know as statistician. If you give me any variable and you want prediction, okay? So I need to know, like, you're predicting Y from X, and Y is a continuous scale variable. So it's a linear, most likely linear regression, okay? And it's a multiple regression if you are predicting Y from many X's, or you are controlling for the main X from other X's. That's how I think about it. And okay, so I need to give you model parameters like predictions. How much change in X leads to change in Y, okay? Then you just name the variables. Variables can be from any field, from anything, from any area or domain. Of course, if you have a categorical outcome, you're predicting a categorical outcome. I start thinking of logistic regression, logistic models, etc. So we have causal research questions. I'm sorry, let me read the script. Does predictor variable X predict outcome variable? In setting, explain where you are observing this, or in what setting X predicts Y, if applicable. Causal research questions, they usually involve manipulation of independent variable. Of course, in experiments, okay, you manipulate, you're doing an experiment. So if I'm trying to now see what works for coronavirus, you know, COVID-19, using an experiment, say this is a hypothetical situation, of course, and then I have two groups, and I have like two drugs or two medications, and I'm trying to see which one is more effective. So I'm giving group A this medication, group B that medication, something like that. This is manipulation, you know, I'm changing things. I am doing something at location A, and I'm doing something different on location B. Of course, when you talk about experiments and you have a human subjects, ethical things come significant. They become very significant, okay? But I think as engineers, maybe you don't need to worry about that. What you need to worry about, causal research questions happen when you have manipulation, when you are doing an experiment. Does variation or change in independent variable? So independent variable can be production method that you are changing, manipulating across different sites. Produce changes or increase, decrease in a dependent variable, okay? So the method, and think about production rate as an example. So, sorry about this, okay. Design the study, yes, I think we are here now. So type of quantitative designs. When you now put the design of your study, you need to ask yourself, what design is good to answer my research questions? And I'm what looking for? Experimental designs. This is experiments and the procedures and protocols, techniques associated with them. Quasi-experimental designs. So quasi-experimental designs are methodologies used to make not completely experimental data experimental, or not experimental design. Not experimental design, you don't do any experiment. By the way, in science, the strengths of evidence, the strongest is experimental design. You cannot really rule out cause and effect, what is causing what, until you do some experiments, experimental research, or at least quasi-experimental. In non-experimental designs, you cannot really say X is causing Y. You can say, I have some intuition about relationships. I can see relationships between X and Y. I see Y works like this when X changes like that, but you cannot really say X is changing Y. So basically, these are the three main quantitative designs. And I think in future lectures, we will talk about these in details, but these need time, to discuss them and give them what they deserve, because each one got some statistical methodologies that you need to use. Okay. What else we need to worry about? Data collection methods and instruments. So how you are going to collect your data? Are you going to use some instruments like some machines, robots, or are you simply going to buy data from an agency or a company that collected the data for researchers to analyze? This is called secondary data sets. Are you going to run a survey? How you are collecting your data? Sample size issues, okay. So in statistics, we need to worry about sample size because you need that to have valid results and to generalize your results. So you need to think, what is the sample needed to have effective results, or like results that can be generalized? So part of my job, I worry every day about sample size calculations for different studies and different models. So a researcher would come to me asking me, I'm running this experiment. The experiment is expensive to run, right? And it takes time and money. And I need to have an accurate number of participants, okay, to have a good study. So you need to worry about that. And you should predict problems in your data, if any. Like, are you going to have missing data, missing cases, and what you are going to do about that, for example. And you should have like a plan about analyzing the data. What's going to be descriptive? What's going to be comparative? What's going to be relationships? What's going to be prediction? And you write a plan how I'm analyzing all this data set. Remember, guys, the purpose of the scientific method is to provide an objective and unbiased collection and evaluation of data. That's the purpose of the scientific method in general. Following the research process steps I just talked about, make your project, do not make your project, flawless. So these methodologies, okay, or these steps and techniques will just help you reduce error. But no research project is completely perfect. And research, another thing, we are not trying to prove things or anything. We are just providing tentative evidence. Many people think when they do research, they are proving things. No, proofs are just for mathematics, but in research, we are just providing tentative evidence. So the evidence you provide today might be like not good tomorrow, or some other scientist will come and say it's missing something, etc. So we are humble people. In research, we are trying our best to provide tentative evidence about how things are happening. So now, guys, thank you. That's all for today. To be continued. We will talk more about things in depth if we have the chance, but I will leave like time to answer your questions if you have any. Thank you so much.
Thank you so much, Dr. Hasan. We all would like to thank you for the amazing webinar you presented today. We have received many questions, but I have collected the most important ones. The first question is, what's the difference between the positivism and the postpositivism?
Okay, that's a good question. So the first question is about what's the difference between positivism and post-positivism. Positivist people, they depend heavily on observation. You observe phenomenon, you look at what you're seeing, you take notes like Isaac Newton, you know? We love Isaac Newton, the father of calculus. So basically observe the world, okay? Think how I can describe the stars and the movement of the star and everything. Okay, I need to make observation, and he came up with calculus. Yeah, that's great. Positivism, it's a scientific method of observation, measurement. You don't need a theory to start. But in post-positivism, theories developed by previous scientists guide your thinking. So you are not thinking independently. You are using the theories in your field or in your area, like evolution in biology, you know, that's a theoretical framework. So if you are working on like biological research that has to do basic research in biology with evolution, you cannot ignore the theory of evolution. For example, you know, by the way, I don't know about the theory of evolution a lot, but you need to look at theories by previous researchers and consider them. So if I'm working on petroleum engineering, I'm a statistician. If I'm positivist and think like, okay, I'm going today with you guys to the oil well location, I'm positivist, remember? I look at what's happening. I look, you start telling me, well, this is an oil well, this is a reservoir, this is extraction, this is fluid pressure, this is gas pressure, this is. Then I start to make research questions, okay, and start to answer them. Now, post-positivist people tell me, hey, hold on, you know, you are ignoring all the work of great engineers before you who did like a lot of theories and a lot of models and a lot of things. So that's the main difference between them. Post-positivist people, you know, they use theories, theoretical frameworks to answer research questions because they think you would be lost in your observations and data collection if you don't use what's written before you. So that makes sense, right? In some examples.
Thank you so much. And the second, I think yes, but we cannot like receive answers from them. I have another question. The question, someone is asking, what exactly is the null hypothesis or hypothesis test? How do that work? And
yes, I will give you a very good example about the null hypothesis and hypothesis testing. So say now I'm happy about my lecture. This is a joke example, by the way, okay? And I'm claiming that, you know, my lecture will significantly improve student knowledge and research and designs, you know? And I started to go, you know, my lecture is the best in the world. Okay, we can measure this scientifically. So let's try to do this, okay? I will tell you, we need a sample of the population. It's you guys attending the lecture, right? And I will test you before the presentation. Let's say we have a test. We designed a test that can really measure quantitative research skills. And you take my presentation and I will test you after the presentation, okay? So this is, by the way, a causal comparative design. I'm comparing a categorical variable, time, before the lecture and after the lecture, and see if there is important significance difference in your scores. Now, before we talk about this, you understand the experiment? I hope, yes. So I'm saying my lecture is great. Your scores will increase significantly. Pre-test, my lecture, post-test, 2 points of time. So this is the categorical variable. Point of time 1, point of time 2, and then the test score is the variable we are testing. So we assume there is a population mean for students, like the population. What is your population, guys? Engineering students. Not only you, this is the population, all engineering students. So say if we test now engineering students, we have a magical method. We can test every engineering student in the world and research method, okay? Using the test we designed. We will have a population mean, right? and standard deviation because I tested the entire population. Oh God, so I have the mean of the entire engineering student population in research design. Say this mean is 65, okay? So, oh good, 65 is the mean of the population. That's nice. This is testing every, again, engineering student. So when I do sampling, of course, in experiments, I cannot get the entire population, or in statistical tests, I cannot get the entire population. I need a sample that is randomly selected from the population, and it will hopefully get a mean close to the population mean. Like say I sampled you guys, and your pretest score was 64.5, for example. Well, that's pretty close to the population mean of 65, right? Okay, so I'm happy. My sample mean is close to the population mean, okay? So now if I change your mean by my lecture, I can generalize it to the population and say, okay, if my lecture changed the mean, increased the mean score of this group, your group, that means it will change the mean of the entire population if given the same lecture. I hope you understand this example. So that's the reason for sampling. Okay, now I gave you the lecture and your mean increased to 95. Wow, 95. So your mean was like the population mean, close to it, 64, around 64, 65. After my lecture, your mean changed to 95. Now, the research question I'm testing using probabilities now, is this observed difference in mean from 64.5 to 95 is the result of chance, or there is something that happened that led to this mean increase? That's what I'm testing really. Is this mean difference from 64 to 95 is the result of chance, like just random, not because of method, or if it's not the result of chance, it's most likely my lecture. Wow. Now, the null hypothesis tells you, okay, the difference between the observed means, okay, there is no difference between the two observed means. No difference. Always the null hypothesis, H sub 0, okay, states that, okay, there is no difference. There is no difference. Now, if this observed difference from 64 to 95 lies, okay, lies in the outliers of the distribution, okay, like this outlier is not likely, then we reject the null hypothesis. I say, no, there is a difference, okay? So the observed difference in mean is the result of my experiment, of course, provided that I did an experiment. So again, to put that simply, the null hypothesis state the observed differences, okay, are not significant. There are no real differences. That's always the null hypothesis. And I'm happy to visualize it for you in coming lectures, because I think really when it's visualized, it's great to understand. But it states no difference. So there is no difference between method A and B in oil extraction. There is no difference between production rate and pressure. It's always no difference between A and B, no difference between X and Y. It states no difference, okay? But what you are trying to do is either accept it and say, yes, there is no difference, or reject it, there is difference. I hope that would answer your question somehow.
Thank you so much. And the last question is, what is the big difference between applied research and action research? And please, if you can give us an examples.
Yes, absolutely. So applied research is general. Like basically, I am trying to find solution to engineering, like in the field turnover rate. Like say a colleague engineer told me, you know, there is like a high turnover rate. Turnover rate mean people quit, okay? Their work, when they work in like the middle of the desert, in oil fields, and that's very big problem to industry and companies. Like as a researcher, he came to me and asked me, we need to investigate this. We need to look at this, why there is this high turnover rate and what we can do to help solve the problem. Now, in applied research, you are interested in solving the problem, maybe in oil, United States, say, for example, oil companies, okay? You're trying to find some solution to this problem using psychometrics, psychological theories, and all of that, and investigating the environment, etc. Action research is concerned with your own company. When I'm working in X company, and they told me we need to solve, the problem in our company. Now, why people nowadays like action research? So it's the same like applied research in this example, but you are limited by your company or context. So they tell you when you talk about all the companies in the United States, you will miss something. You will not provide solutions that fit everybody because every company is different, It has different context, it has different policies, it has different ideas about employment, HR, hiring. So what we need to do, this is action research philosophy, instead of investigating phenomena, holistically or in big population, focus on your company, focus on where you work, focus on the natural context of the problem. Like, for example, like we do an evaluation, like we say how we can make universities better. This is like some applied research, right? Idea. But how I can make my university better, this is action research. So that's what I'm doing. I'm in action. You are taking action through research to improve your community you live in, your company, your institution. While in applied research, you are more interested in the general thing. That's the main difference between the two.
Thank you so much, Dr. Hasan. I would like to thank you on behalf of all of the students and organizers of this internship for the great webinar you gave us today. And thank you guys for attending, and see you in the next webinar. Thank you so much.
Thank you so much, and I'm happy I presented to you guys. Take care and let me know if you have any other questions. Bye-bye.